So question 4 was about forces and differential equations. So there's a ball of mass m and it's projected with an initial velocity of 15 meters per second downwards into a tank of water. It travels through the water against an upward buoyancy that is 4 times the magnitude of the weight and a drag force of mv squared newtons. We're asked to draw a diagram to show the forces acting on the ball while it's moving downwards, which is important, as you'll see in a second. So we'll draw the ball. So of course, anything that has mass, we're going to have its weight, mg. Going upwards then, we're going to have the buoyancy, an upward buoyancy force that is 4 times the magnitude of the weight, so it's going to be 4 mg. Now the drag force of mv squared newtons, remember that drag forces always oppose the motion of an object, so the drag force is going to be going upwards because the object is moving downwards. It's projected vertically downwards into the tank of water. So now we're asked to show that while it's moving downwards, the rate of change of velocity v with respect to distance s below the surface of the water can be expressed by this differential equation. So remember F equals ma, and that's going to be the sum of all the forces. So now we have two options. We can take downwards to be positive or upwards to be positive. Now we're going to take downwards to be positive, but let's just see why. So you can see here, v in the equation that we're given, v dv ds, that's the same as acceleration, that's a. And that's going to be negative, because v squared will always be positive, and that minus 29.4, that's a minus and a minus, it's always going to be negative. So that means the acceleration is negative, and if we have a look in this diagram, well, overall, the 4mg and the mv squared, they're going to be stronger than the mg by itself. So it's going to have a net force upwards, which means it has an acceleration upwards. And since that acceleration has to be negative, upwards has to be negative. So we'll say that ma equals, and now upwards is going to be negative, so we'll have minus 4mg minus mv squared. And now since we're taking downwards to be positive, we'll say plus mg. Now we can simplify a few things. Those m's are going to cancel if we divide across by m, and we get that a equals, now minus 4g plus g is going to be minus 3g minus v squared. Now a equals dv over dt. Acceleration is the rate of change of velocity, and we can get the form they have up here by multiplying by ds over ds. Now, of course, technically, we're just using a trick here. They're not actually fractions, but this is an easy way of thinking about it. That means if a is going to be equal to, and we're going to group some of these together. So we're going to group this ds with this dt, and we're going to group this dv with this ds. So we're going to have the ds over dt multiplied by the dv over ds. Now ds dt, that's the rate of change of displacement, that's just velocity. So that means that a equals v, the velocity, multiplied by dv over ds. So we can replace the a in our equation with that, and we get that v dv ds equals minus 29.4 minus v squared. Now we've shown what they wanted us to show. So now we're asked to solve the differential equation. So first thing I would do is I'd multiply across by ds, so bring that ds up to the right, and divide by the minus 29.4 minus v squared. So we'll get v over minus 29.4 minus v squared. So I just brought that down, and the dv stays there, and then I bring the ds over to the other side. Now just to make things a bit simpler, I'm going to take out that negative there, and so I'm going to write it as minus v over 29.4 plus v squared dv equals ds. You don't have to do that, but it just makes the calculations a little bit easier. So now we'll get minus the integral of v dv over 29.4 plus v squared. That's going to be equal to the integral of ds. Now we could plug in limits here, but because we're going to have to do a u substitution, I think it's just easier to do the method where we have a constant and then just solve for the constant. So we're going to focus on the left side because that's going to be a bit harder. So we see we have a v squared on the bottom, something plus v squared on the bottom, we have a v on the top. If we do a u substitution and let u equal to the bottom, we can get those v's to cancel, as you'll see here. So let's say let u equals 29.4 plus v squared, which means that du dv will be 2v. And now we can solve for dv to get rid of the dv. So we can say that dv will be du over 2v. So now we can rewrite minus the integral, and we're going to have v over, well, the entire denominator is just du, multiplied by, and then the dv is just du over 2v. And And that's going to be equal to the integral of ds is just s. And we're not going to do the plus c yet, we'll just do that at the end when we're done with all the integrals, because we can just take all the plus c's and put them into one c, because a constant plus a constant is just another constant, it doesn't really matter. So we can see here, there's a v and a v are going to cancel, and that 2 on the bottom, we can take that outside the integral, so you have minus a half times the integral of 1 over u du, that's equal to s. So that'll give us minus a half times the natural log of the absolute value of u, and we're going to add the plus c now, and that's going to be equal to s. Now we can put back in what our u was. U is 29.4 plus v squared, so we can say minus a half times the natural log of 29.4 plus v squared. That's going to be equal to s, plus c equals s. So we don't need the absolute value, because 29.4 plus v squared is always going to be positive, because v squared is always positive. And then we can multiply both sides by minus 2 to get the ln by itself and bring the c to the other side. So we'll get ln of 29.4 plus v squared. That'll be equal to minus 2s. And then plus c, it's going to be multiplied by minus 2, and it's going to be brought to the other side. But at the end of the day, it's still just a constant. We're just going to write plus c. Now we can do e to the power on both sides and say that 29.4 plus v squared, because e to the power of ln, they're going to cancel, equals e to the power of minus 2s plus c. Now we can separate that out, so keep the left side the same, 29.4 plus v squared. That's going to be equal to e to the minus 2s multiplied by e to the c, because that's one of the laws of indices. And e to the c is again just a number, so we can just write c. So 29.4 plus v squared equals some constant c times e to the minus 2s. Because again, that c, it's e to the c is just some number, which we're going to call c. It doesn't matter. And now I think this is a good time to solve for c before we start taking square roots and stuff. So we know the initial velocity is 15, and at that point the distance traveled is 0, because that's at the start. Now, just to make sure, remember in our diagram we took downwards as positive, so the 15 meters per second is going to be positive because it's going downwards. So v equals 15 when s equals 0. So then we're going to have 29.4 plus 15 squared is 225. That's going to be c times e to the 0, and e to the 0 is just 1, so that means that c equals, and we just add those together, c equals 254.4. So now we can just go back up to where we were here, and we can just replace the c with that number. So 29.4 plus v squared, that's going to be equal to 254.4 times e to the minus 2s. Now, finally, we're asked to find an expression for v in terms of s, so we'll bring the 29.4 to the other side and take the square root, and we get that v equals the square root of 254.4 e to the minus 2s minus 29.4. And that's it. If you want, you could write the e to the minus 2s as 254.4 over e to the 2s. Doesn't really matter, it's just a bit neater that way. And yeah, that's it. So now we're told that the ball is at its maximum depth when v is 0. So we're just going to sub that in. So when v equals 0, s will be d, the distance d. So we can say 0 equals the square root of 254.4 e to the minus 2d minus 29.4. Square both sides, bring the 29.4 to the other side. We get that 254.4 e to the minus 2d equals 29.4. Then again, we're just skipping steps. Divide by that 254.4, take the ln on both sides. Minus 2d will be equal to ln of 29.4 over 254.4. Then finally divide both sides by minus 2, and we get that d equals minus a half times the ln of 29.4 over 254.4. Throw that into your calculator, and that gives us an answer of approximately 1.079 meters. And that quantity is positive because remember we took downwards to be positive, so it's 1 meter downwards, just over 1 meter. Then the ball will be moving upwards, so it's going to be very similar. We're asked to draw a diagram to show the forces on it now. So we're still going to have the mg going down. We're still going to have the buoyancy force going up of 4 mg. But now since it's moving upwards, remember drag always opposes the motion. So that means if it's moving upwards, drag's going to be going downwards. And remember drag is mv squared. And in the final part, we're asked to write a differential equation for the rate of change of velocity while it moves upwards through the water. So now we actually doesn't matter which way is positive and which way is negative because they didn't tell us to put it in a certain form. It can be whatever what you want. So I think in this case, it's easier to take upwards to be positive because that's the direction it's going to be moving in, which makes the most sense. So we're going to have our MA again. So MA equals, and upwards is going to be positive. So 4mg minus mg minus v squared, mv squared, sorry. Again, we can divide all those m's away, which means that A, and remember A is just dv dt, the rate of change of velocity with respect to time. 4g minus g, that's going to be 29.4. We're going to have minus v squared. So the only difference is that one of the things changed signs, which makes sense because the only one thing changed direction when it went up, and the only thing that changed direction was the drag. So yeah, that makes sense. You could have v squared minus 29.4 if you decided that downwards would be positive. That's what you would have gotten, but both are correct technically since it doesn't specify.